Yeah, this is we're going to discuss a tool that we built. This tool is called MyCam, which stands for Model Integrated Cam Visualizations. Basically, what it does is it gives a full cam diagram for every level within a convolutional neural network. Background: we use convolutional neural networks to examine digital data, and we're looking for bad actors. We looked in particular at process metrics from an application server. This application server was in the cloud environment, and we injected malware into it at 15-minute mark while taking service logs. And from these logs, we have for every process metrics, and we apply these in the grid, and we analyze it for seeing if we can find the malware as it's running on the machine. We also took a look at TCP/IP sessions from the CICS-IDS dataset using the same process. And we found that statistical correlation was better than the average ordering scheme. And just to give you an idea, this is basically statistical correlation. And what we did was we developed a process to use this function to order our grid. Our grid has, like every image, you've got pixels. Your pixels are in an order in an image, but in digital data, what is this order? We used the log order in most cases and the initial settings, and we found we got about an 87% percentage rate of solution. When we used statistical correlation, we were able to improve this up to 99%. So, but that all depended on the models. And these are some, we use different correlation schemes, and we show that some models really appreciated correlation, whereas other models didn't. And we were wondering why. And so we looked at different visualization tools to see if we can use some visualization tools to identify what these images are doing, what these convolutional neural networks are doing when they're identifying, and why one order works versus another. And here we are. We have some visualization diagrams of a dog being analyzed between dogs and cats, and this is for on a shallow network. And you can see the visualization tools. They give you some idea of what the convolutional neural network does, and it's got some relationship to the original image. And so we were like, okay, maybe we can use these to see what's going on inside these different convolutional neural networks. Maybe they give us some idea of what's going on. And so here's ideas. Here's some different samples of the images that we were sending them. This is two data samples of process metrics. And you can see on the top one, we've got correlated rows and columns. And you can see how we've got images, the objects are really dense and bright. Whereas in the anti-correlated, we kind of spread things out. And so what we did is we ran these visualization tools on these. And we can see here that these visualization tools on every one of these networks really end up giving different results, and you really don't understand, they're not interpretive. You can't really see what's going on. And so we decided to get a little deeper. And the reason for this is, first of all, they're black and white images. They don't show any real depth of color. They just use color eyes to make it a little brighter. That's really all they do in their image development. And they're also only examining the Panelto layer. And in convolutional neural networks, these Panelto layers are actually quite small. With our input data being 150 by 75 pixels, the resulting Panelto layer was usually like 2 by 4 or 3 by 6, which means you really don't get a lot of granularity from the original image that's being supplied. And so we decided to design this MyCam, this thing where we actually take a cam for every layer, whether it's a convolutional layer, which we actually design cams for, or whether it's one of the pooling layers, and so that we can actually see every step as the individual pixels or filter layers, filter objects are modified, and we can get a much better detail on what's going on inside the layer. When it comes to color, we actually used 4 of our layers for the schemes. We have alpha, red, green, and blue, or transparency, red, green, and blue. And we use that to help generate deeper images so we can identify what's going on. In the blue spectrum, we basically only take all the positives, everything from 0 to 255, and we take the whole range of data, because some of the data was negative, some of the data was positive, and it would be at a different range. Well, to get our color scheme, we go from 0 to 255 for the full range of data for blue. For red, we only use the positive values. So when we get purple images, it's going to represent positive values in the convolution. And we use green for negative. And so when we get kind of yellowish values, it tells us that we have a negative, or greenish values, it tells us we have negative values in our layer. And then finally, we use size, and we use size and alpha to represent comparisons in between the layers. So when we have a layer that has large pixels and are very strong, that represents very strong values compared to the other layers, which probably had minimal values. And here's some examples of using the MyCam on the MNIST data set. We've started there, so we can take a look at images. This is looking at a 7. And you can see here a Linnet 5 and a Resonant 18, different layers. And in the red Linnet 5, this is the entire network. And you can see how the pooling layers are gathering in this here and this here. It's the pooling layers that are making the extracting the features for later on for the convolutional and the dense layers to make decisions out of. And it's the same thing here, but in here, Resonant doesn't use pooling layers until the very last thing. So your extraction layers are ending up with these quite varied pattern-looking objects instead of pooling, which is extracting individual highlighted pixels. And you can see down here that the how the final convolutional layers or the final pooling layers are making decisions on 7. And it's actually kind of interesting because this mark here, 7, is the same. And if you use different numbers, they go back and forth, and these different layers actually show different values when you have different numbers. And the 3s are all look the same, and the 7s all look the same. So you really get a very strong sense of what the value is based on where these pooling layers are. And then here's a dense net. Now this, I'm only showing a handful of the layers. Dense net, the number of layers is like 250 something. And so here we only have a handful of them. And I'm looking and specifically where we have dense connections and analyzing how the dense connections bring in the data from the previous split, where you can see how the data is, being analyzed, and then the dense connection reinforces the original data so that you don't lose that granularity. And as it goes down, you can see how you've got the pooling extraction layers also are generating our features. And it's from this analyst that we actually decided that it was the pooling layers that were making the decision, because in the earlier in the model, if you have a pooling layer earlier in the model, statistical correlation works very well. But if you have pooling layers later in the model, you want to use anti-correlated and spread that data out. Now, I do have all the code and many, many more images, both of MNIST data and of the digital data that I'm going to be sharing with you here in a second. Now, here's some examinations of the digital data that we looked at earlier. And this one here is looking at a benign sample and an infected sample. And in this situation, we're seeing the best and the worst. And you can see how the best, you've got brighter blues, brighter whites that are showing strong values. Whereas here, you've got stronger greens or reds in the worst one. So there's definitely a difference. And then down here in the pooling layers, you can really see the difference in the pooling layers, whereas the pooling layers in the best scheme are making really bright, strong identifications of features that are getting extracted, whereas in the worst order, it's not so much. This is real similar to what we see also here in the with the resonant plots. Again, we're seeing some bright items here in the areas when you compare the worst versus the best, which basically tells us that the better the better order is identifying these features much stronger with much more clarity. And then we can also see down here in the pooling layers, how the pooling layers in the best order are a little stronger and a little different between the benign and the infected sample. Whereas over here in the worst order, there's a little bit more similarities between them. So it makes it a little bit harder to differentiate. Another interesting thing is if you examine, you can see that there are individual, let me see, was it this one? Yeah, up here, higher layer in the layers, you can see these data points that are really, really bright, and they might give us some inclination on where in the data we're identifying good and bad guys. So we also looked at the CICS data set, and this was our overall determination on it. We show the correlation majority. We also took different sample sizes of our CICS data set because they were classified by malware or by attacks. And so we did correlations on these different sample sets to identify individual orders, trying to say focus on one individual classification of malware to see if that had any improvement on the overall analysis on all the malware. And we showed that generally using correlation for really any subset except for very small subsets, because this is like very, very small percentage of our overall data, or just the benign subsets didn't work well. But really all the other subsets generally work pretty well. And here's a comparison between our worst and best using the MyCam. And this is using on a Linux 5 model. And you can see in the worst order over here, these pooling layers are less bright, whereas in the best order, they're much brighter and they're showing more, more clarification of what's going on here. Anyway, that's generally the whole thing. If you, the future is I've got this code out there. It's available for anybody to use. If you want to generate MyCam diagrams for any kind of convolutional or deep neural network that you guys have, feel free to take the code. It's out there and publicly available. That's it. Any questions?